everyone, today I'm going to be going through the worked examples from 5.2, which is a review of differentiation. This is a pretty long video, I think, because there's quite a lot to get through, and I want to explain first principles in a little detail as well. So let's use example 1 to do that. So we've got the function f of x, and they're asking to sketch that graph and to show all the important features. So look, I won't take too long in sketching it because that's sort of not the point of this exercise so much, and we should all know how to sketch parabolas by now. So we'll have x-intercepts. Y equals 0, so it's x plus 2 and 1 minus x. Of course, null factor law, so x plus 2 equals 0, x equals -2. Just look, be careful with this one. Look, people will get it wrong. It's not hard, it's just sort of a bit of a weird one, I guess. So we've got x-intercepts and 1 and -2. So 1 and -2, 0. And of course it's a sketch, so it's not going to be 100% accurate, but I have made it as accurate as I can, for the purpose of the sketch. The turning point is going to be in the middle of the two x values, so the x value of the turning point is going to be -1 plus, no it's not, it's going to be -2 plus 1 over 2. -2 plus 1 is -1/2. And then to find the y value, we can just sub that in. So -1/2 plus 2, which is 4 on 2, times 1, which is 2 on 2, minus -1/2. And again, be careful there's a double negative, so people could stuff that up. -1/2 plus 4 on 2 is 3 on 2, so 3 on 2 times 2 plus 1 is 3 on 2. So that's going to give us 9 on 4. Of course, we multiply top and bottom, and well, I guess you could break that down into 2 1/4, but I'm not going to do that. Improper fractions are just fine, but of course you simplify. So -1/2 and 9 on 4. So there's our turning point, and then it's just the y-intercept. So y-intercept, x equals 0, so 0 plus 2 and 1 minus 0 equals y, and that's going to be 2 times 1 equals 2. So our y-intercept here at 0, 2. All right, so there's my graph. I'm not really sure why they ask us to do that in such detail. Maybe the next part of the questions will give some context, but I feel like it's a bit of a waste of time just sketching the parabola there, which we should already know how to do pretty well. Let's move over here, so we've got more room. So now if P is the point x f of x and Q is the point x plus h and f of x plus h, find the gradient of the secant PQ using first principles. All right, good. Here's a first principles question. So what I'm going to do, I'm actually just going to draw this again, and I'm not going to draw all the features of the graph. And in fact, I don't want to draw all the features of the graph for this question. I'm just going to exaggerate the gradient a little bit so it's easier to show. So first principles. This is what happens. You've got a point, and this point is called x and f of x. Why is it called x and f of x? Well, because f of x equals whatever the equation is, and in this case it's x plus 2, 1 minus x. And look, I'm going to expand that. X times 1 is x, x times neg x is neg x squared. 2 times 1 is 2. And 2 times neg x is -2x. So f of x is going to be -x squared. X minus 2x is a neg x plus 2. So if I was to put a point, if I was to say x is 1, for example, you would know that if x is 1, then you'd be subbing the 1 into all your x values, and you would find the corresponding value of y. So how we would get the y value or the f of x value is by subbing the x into that. So when we see the first point on our, when we're using first principles, here's x, it's any value. It could be a 2, it could be a 3, it could be a 1. And then f of x represents when we sub x into this equation. So really, I mean, I could write this as x, comma, negative x squared minus x plus 2. And look, that's what I'm going to do. I'm going to leave it like that. So that's my first point, and that's P. And then the second point is going to be Q, and there it is here. And it's got this plus H thing here. Well, what is H? You may well remember from year 11. Actually, we will use a different colour. H is the distance between the two x values. And look, I'm going to make it quite large just so we can see a little bit more clearly. H represents the distance between the two x values. So this is x. And if x was 1, then just say h was 3. That would mean that, just say x equals 1, h equals 3. That would mean our x plus h would equal 4. So x plus h is just adding a unknown distance to your original x value. So I'm going to rub out those 4s, the 4, 3 and 1 there, because obviously they're not those values. I'm just making it up. But hopefully that gives you the understanding of why this is called x plus h. So let's say our x plus h is here. So now our x value for Q is x plus h. And well, if x plus h was 4, like we said before, well then in order to find your corresponding y value or f of x value, you would be subbing x plus h into your equation, your f of x equation. So I'm going to write that out, f of x plus h. And look, it's just quite nice to put it into this one here rather than the bracketed one. You'll see as you do them how it is just easier to work with if you expand first. So I put x plus h here, squared. The negative is not in the brackets with the squared, so just be aware of that. Minus x plus h plus 2. So now if I expand that, and I will expand it at this point, this is, a squared plus 2ab plus b squared. So x squared plus 2xh plus h squared. Excuse me. Excuse me again. Negative x, negative h plus 2. And I would say one of the most common places that people will stuff up first principles is when they get the negatives stuffed up. So just be really on the ball with how you're using negatives. So now I will collect any like terms. So I've got neg x squared. Well, I don't think we have any. So that's the end of it. So now I can say, well, my y value, which is quite an extreme y value there, or f of x plus h value, is neg x squared minus 2xh minus h squared minus x minus h plus 2. So these are my 2 points, P and Q. And, well, if you've got these, then really finding the gradient of the secant from first principles is really easy and makes sense. And I'll show you why. Because the secant is the straight line that connects those 2 points. So the gradient of that line, the gradient of the secant, PQ, is going to be, well, just like your usual gradient, y2 minus y1 over x2 minus x1. Well, we've got our 2 points, just like any 2 points. If this was 1, 3, and this was, we'll make it a negative, and this was 4, 1, then you'd say y2 minus y1 over x2 minus x1, and you'd find the gradient, just like you did in probably year 8, and that would be really easy. It's the same thing, only that our y2 is this great big thing. And my suggestion to you, even though it won't matter which one's x2, y2 and which one's x1, y1, I put the more complex thing, so this obviously is more complex than this, So I'd make the more complex thing be y2, and of course that has to be x2 then. So of course x2 and y2 are together, and x1, y1 are together. And what I notice is a lot of people will stuff up which one's x1 and y1 and which one's x2 and y2. So they'll do like x1 and y2 together. So if I were you, I would just label them as I've done here, because then you can just avoid that really quite silly mistake. So let's do it. So y2 is neg x squared minus 2xh minus h squared minus x minus h plus 2. And now we're going to subtract y1. I'm going to put it in brackets. And you absolutely need to put it in brackets because you've got to subtract all of that, not just the negative x squared. So neg x squared minus x plus 2. All right, so that's y2 minus y1 over x2, and our x2 is x plus h, minus x1, and that's just x. You don't need brackets for that. It's only one thing. And now, so we can say the gradient of the second, which I guess we can say f neg, no, definitely not f neg 1 of x, f dash of x, is going to be, let's cancel, negative x squared, I might use a different colour. So neg x squared minus minus, that's plus x squared, so that's going to go. What else? We've got negative x here, so we've got negative x minus minus x, that will go. 2 minus 2, that will go. So what we're left with here is negative 2xh minus h squared minus h over x minus x is 0, so it's just over h. So at this stage, while we're going to get f dash of x is going to be, let's cancel the h's. H divided by h is 1. Be careful, a lot of people will cross that out, and what will happen, I'll just do it wrong first. That will go. So a lot of people are going to get the answer negative 2x minus h, and they're going to forget that when you divide h by h, it equals 1. So this equals 1 as well. But if it's in the denominator, when you divide by 1, you of course don't need that. But in the top, of course you do. So it's going to be minus 1 here. So our gradient function, or gradient of the second, is this. And I'm just going to write gradient of the second, PQ. So this equation, f dash of x being neg 2x minus h minus 1, represents the gradient of that straight line connecting P and Q with any distance of h. So if you want the distance of h to be 7, then you'd be subbing a 7 in. If you want it to be 2, you'd be subbing a 2. You really want it to be as small as possible because we're going to be finding gradients at the point, but we'll deal with that in the next part of the question, I think. Yeah, so we've found the gradient of the second using the first principle. So that's part B done. So let's now move along here. Actually, I might move this over. That's better. All right, so if P is the point neg 2, 0, determine the gradient of the tangent to the curve at x equals negative 2. All right, so let's see what they're talking about. And you don't need to draw two different representative diagrams, but I'm just doing it here again so we can see. Again, I really find that part A of this question was a bit of a waste. We shouldn't need to be, finding, the key features of parabolas at this stage. And considering the exercise is so long, I don't know why they've made us do that. If P is a point neg 2, 0, okay, neg 2, 0, so that's this. Determine the gradient of the tangent to the curve at x equals negative 2. All right, so let's draw what that means. So the tangent to the curve at x equals negative 2. Well, the tangent is the line, and I'm going to use the ruler here, which goes through the point, and I'll get rid of that. There we go. So this is the tangent, so it's not a great representation, but it touches the curve. So it doesn't go like this. It doesn't do that, it just touches the curve. And we should really know what a tangent line is anyway. So what we now need to do is say, well, if x is negative 2, then we want to know the tangent at that point, and we can use our f dash of x equals, what did it equal? Neg 2x minus h minus 1. Ah. So this is the gradient we found for the secant PQ. And in our first, or our second part there, I drew the secant PQ was quite long. So the value of h was pretty big. And you can see that the gradient from here to here, well, it's going to be representative of the gradient exactly on P, but not so much if it's so long. The shorter that line gets, so if I put my Q value, if I put Q here, then the line connecting P and Q, the gradient of that will more closely represent the gradient of P. As the value or the distance of H approaches 0, so as H gets so short that it's like 0.00001, for example, your value of Q is basically on top of P. So the gradient of the line of the secant between P and Q is going to be very, very much representing the gradient exactly at P. So what we do, and again you probably remember from year 11, we say, well, we make a limit as H approaches 0. So H won't equal 0, but it's very, very, very close to 0. And we can say, well, the limit as h approaches 0 of neg 2x minus h minus 1, and I'm just going to make h equals 0 there, so equals neg 2x minus 1. So of course it just cancels out the h there. And then our final thing is to say, well, our gradient is going to be when we want x to be negative 2. So we're just subbing negative 2 into the equation, into x. So neg 2 times neg 2 is 4, 4 minus 1 is 3. So the gradient at that point is 3. And notice 3 is very different from 0. So this point here with the y value of 0, we've got 3 pieces of information. The x value is negative 2, the y value is 0, and the gradient is 3. All right, so that completes example 1. Let's move to example 2. Okay, so these ones are far quicker and easier. So this is just reminding you how to differentiate, not from first principles, the quick and easy way. And just to point out, look, the chance of you having to do first principles in an exam or SAC or something is very, very low. But you could check that you were correct by just differentiating in the normal way. So we expanded this equation somewhere. Yeah, over here. So if f of x is neg x squared minus x plus 2, then differentiation, remember, you multiply by the power. So negative 1 times 2 is negative 2. And then you minus 1 from power 2 times 1. 2 minus 1 is 1. So we don't need the 1 there, but I'll just put it there to show you it became 1. And then this is 1 times neg 1 is negative 1. X to the power of 1 minus 1 is 0. And anything to the power of 0 is 1. So that means 1, it's times 1. So our gradient would be neg 2x minus 1. And indeed, that is what we saw when we got to the third part there, neg 2x minus 1. So you can always check, if you do have to do first principles, you can check that you're right. So if you do make any little mistake with negatives or anything, it's easy to see that you've done it wrong. Okay, so let's go example A. F of x equals x cubed, and the first thing to do is to make everything in a line, so you don't want fractions. So it's going to be negative half x to the power of neg 1. So remember, this is in the denominator, so to bring it out of the denominator, it has to change to negative power, plus 4. And then f dash of x, be careful, it's not f neg 1 of x, so it's confusing sometimes because we've been working on inverse functions. Don't get confused with the notation. So we say x to the power of 3, we times 3 times 1 is 3, and then we say minus 1 from the power. Negative 1 times negative half is positive half. X neg 1 minus 1 is neg 2. And then the 4, well, this is x to the power of 0 because it's anything to the power of 0 is 1. 0 times 4 is 0, x to the power of -1, but if you're timesing by 0, well, it eliminates it anyway. So you don't need to show that, but just to point out to you why it eliminates. And look, you may want to put them in one line. And look, I would say it's better to get rid of the negative powers, but you'll see sometimes in the answers they do, sometimes they don't. You'll see what I mean. So maybe practice putting things into moving them across the vinculum to make positive powers, but so that you're comfortable with that. But you'll see sometimes they do one way, sometimes the other. The next one looks a little bit hard. I might actually move it down. Okay, so y equals, this is x to the half minus 3x cubed over 4x squared. Now, later on we learn the quotient rule, and some people would use the quotient rule for this, but that would be a silly idea even once you know the quotient rule, because you can break this down far more easily, and it's really quite straightforward to differentiate when you've got one line rather than use a special rule. So here I'm going to break this down to x to the half over 4x squared minus 3x cubed over 4x squared. And look, you don't need to do this step. If you can see straight away, you could go from that step straight to what I'm about to do. So it's 1/4 x to the power of half minus 2. So remember, if it's a division of indices, we subtract. And 2 is 4 over 2. 1 minus 4 is -3. And then 3 minus 2 is 1, so that's a bit of a boring one. So y equals, and then y is going dy dx. So make sure you call it the right thing. So this one was f dash of x because it was an f of x function. So if we're starting with a y function, you're not going to turn that into f dash of x. Call it dy dx. So that's going to be -3 on 2 times 1/4 x to the power of -3 on 2 minus 1. And 1 is 2 on 2. We'll do common denominator, and this minus 3/4. 1 times -3/4 is -3/4, and x to the power of 0. Okay, let's see. -3 times 1, okay, 3, 2 times 4 is 8. X, -3, -2, -5 on 2, minus 3 on 4. And again, I'm going to put it with positive powers. Dy dx equals -3 over 8 x to the 5 on 2 minus 3/4. And look, if this was to the power of half, you would make it a square root. But 5 on 2, like, I mean, you could do the square root of x to the 5, but it just seems ridiculous. It's no better than this, so I'd just leave it with the fractional power. All right, let's move on. Okay, worked example 3. Let's see. If f of x equals this, what is the gradient of the curve when x equals -2? Okay, it's kind of like the question we did for worked example 1, except we're certainly not going to be using first principles unless specifically asked to do so. So we've got f of x equals 3x to the -1 minus x squared, and we're asked to find the gradient. This is the y function. So in other words, this is your original graph. So we're trying to find gradient, not a y value. We don't, or maybe I should call this, we can say this is the y values are given by f of x. We don't want a y value, we want a gradient value. So last year, well, for year 11, I would have said, if you want to just write gradient there, that's fine. But really for year 12, you really want to call it f dash of x. But if you need to, for the meantime, maybe write both so you can get used to it. And our gradient function is -3x to the -2 minus 2x, which is f dash of x equals -3 over x squared minus 2x. And you'll notice that when you've got to sub something in, it's definitely better to have positive indices. So definitely better than this. So for a question like this, I would certainly put it with positive indices. So now we can say we get the gradient values. So gradient values are represented by f dash of x, and that's our equation to sub into. So we want to know when x is -2 what the gradient is. So, well, obviously we're going to sub -2 in. So f dash of -2 is going to be -3 over -2 squared minus 2 times -2, which is -3/4. -2 times -2 is +4, which is +16 on 4. -3 plus 16 is 13 on 4. So we can say f dash of -2 is 13 on 4. The gradient when x is -2 is 13 on 4. The y value when x is -2 is not 13 on 4. To find that, you would need to sub it into the y equation, the equation that gives your y values. All right, let's see. Part B. Let's move it here. So if f of x is this, that's our y function, so y values are given by f of x, which are 2x to the half. We want to get rid of roots. They're not nice to work with. -4. So that gives us our y values. Determine the coordinates of the point where the gradient is 2. So when the gradient is 2, gradient equals f dash of x equals 2. So, well, it kind of makes sense that we need a gradient equation. So we'll make a gradient equation. And really for all of these, you're going to need a gradient equation. So if you're not sure what to do, your first step, make a gradient equation. And then, A, you might get a clue of where to go from there. B, you might get some mark just for doing that. So half times 2 is 1. Don't need the 1 there. X to the power of half minus 1. And then the -4 will disappear. So f dash of x equals x to the power of -half. Okay, so now, well, this is a negative power. So it's going to be 1 over x to the half. And it would be nicest to write over 1 over root x. So let's see. Now we've got a gradient equation. Our gradient value is given by this equation. So if we sub a value of x into that, we're going to get the gradient. But they're not asking us to find the gradient. They're telling us the gradient and asking us what is x and y when we have the gradient of, what was it, 2? So now we can say, well, this equals 2. So that means 2 root x equals 1. Root x equals half. And square both sides, x equals 1/4. So what this tells us, the x value is 1/4. What people are going to do, which will be wrong, people are going to write 1/4, 2. That's wrong because that is the gradient. What we want is the coordinate, and the coordinate means the y value. So if you want the y value, you're going to have to get the y value from subbing into the y equation. So that is f of what was it, 1/4 equals 2 root 1/4 minus 4. And in this case, it's better to use the square root rather than the power of half. So you have to be sort of on the ball what to use when. It's not always appropriate to use powers in fractions. It's not always appropriate to use the roots. So f of 1/4 equals 2 times root 1/4, so that's going to be 2 times half minus 4. 2 times half is 1 minus 4 equals 3, or -3 I should say. So the point, this is the y value when x equals 1/4, and x equals 1/4 when the gradient is 2. So you don't need to write all this, I'm just doing it to show the understanding. So the gradient equals 2 at the point 1/4, -3. And that's our final answer. All right, let's move forward. We've got 4, 5, 2 more. We're getting there. Okay. The graph of the The graph of the cubic function f of x is shown. Sketch the derivative function f dash of x. Okay, I like these very much, sketching derivative functions. I feel I have quite a foolproof way of doing it. So if you follow along with this, you might find that it works very well for you. So let's see. This is what we know. Step 1, the gradient is 0 at a turning point, or point of inflection. So really, I could have just said at a stationary point there. So the gradient is 0 at the stationary points. So what we'll do, let's set up our axes, and you need to call it dy dx, which is the gradient. In year 11, I would have told you this will do, just put gradient, but for year 12, you want to call it dy dx. And really, you don't even want to write that there. If you need to, for the meantime, by all means do. So this is what it is. We've got the x values on the x-axis. They're still the x values, so they're still going to be in the same place. What changes are the y values. They're no longer y values, they become gradient values on our new graph. So my first, actually this might be my second step. The first step would be set up the axes. And when you set up the axes, you want to make dy dx against x. So step 2, the gradient is 0 at the turning point or point of inflection. So let's find the turning point. Here's a turning point. And what we want to remember is that this is not y. Y is irrelevant. So really we can cross out any y values because they're just not relevant. So at negative 0.2, we've got a gradient of 0. So this is where this point is going to go. Negative 0.2, comma 0. Because now this is an x value and this is a gradient value. It's not a y value. Let's rub that out. So really think we're looking now at gradient, and at a stationary point, the gradient is 0. The next stationary point is here. And again, the y value is irrelevant because we're not doing it against y, we're doing it against a gradient. The gradient is 0 when x is 2.2. So I'll put that here. So there's my second bit. So I've done the axes right, I've done the stationary points. Now I need to figure out which way I'm walking, up or down the hill. So let's see, I'm going to break it into parts. So here's the first stationary point. Here will be up to the second stationary point, and then this will be after that one. So there's 3 things I need to consider. So if I was walking along, so we're walking always from left to right, if I'm walking on this line here, I'm going down the hill. That means the gradient is negative. So I'm going to put a box in the negative zone of this axis. So it's negative. Here's negative, here's positive. Then to get from my first stationary point to the second stationary point, I'm going up the hill. So that's a positive gradient. It doesn't matter that I have negative values here. We're not talking about the y values, we're talking about the gradient. Are we going up or down the hill? We're going up the hill, so it's positive. It's positive all the way from the first stationary point to the second stationary point. And the last bit, I'm going to be walking down the hill, and I'm walking down the hill forever then. So I'm going from the second stationary point all the way to infinity and down the hill, so that means it's negative. And again, it doesn't matter that there are positive values of y. Y has nothing to do with it. We're talking about whether we're walking up or down the hill. Up the hill, positive gradient. Down the hill, negative gradient. So now all I need to do, so I've considered up or down the hill. Step 4, connect it up. So this, I've got to get to here, so it's going to be some sort of turning point. This and this. So it's a parabola. It looks like a little bit of a weird parabola. I might just redraw it. And the points that need to be there are these intercepts, which came from the stationary points. These values here, these x-intercepts on the y function, are irrelevant to the gradient graph. So we're only going to be needing to put those points, stationary points, which then become x-intercepts, and our shape. They're the 2 things that need to be correct there. Let's go to the next one. State the domain of the gradient function f dash of x for the function shown. Okay, for the gradient function. So this is the rule for a gradient. For gradient function to exist, the graph must be smooth and continuous. And I've written many sacks for the first sack where the specific answer is there is no gradient function because the graph is not smooth and continuous, or something to do with that. So it's actually important that you really know that and you can understand that. So let's see, I think the best thing to do is to look for where there will be no gradient function. And you can see here it's not smooth and continuous. It's not smooth and continuous because, well, I guess you can say as you're approaching x equals 1, so here's x equals 1, as you're approaching, so pretend you're walking along the function, well, then you're going to fall through the hole. That's not smooth and continuous. So you expect when you get to x equals 1 that y would equal -2, but it doesn't. It goes to 1. So you have something that's unexpected there. Same thing when you're walking this way. Well, yeah, you do get to 1, and when you get to x equals 1, y is 4, yes, but then you're going to fall off the end there. So this is not smooth and continuous. So we can say there's no gradient at x equals 1. So that's the first bit. The second bit is here. That's not smooth and continuous. It changes to a different graph abruptly there. Or x equals 4. So everywhere else, it's all right. If I can walk all the way from infinity along this graph, all the way up to there. Once I am on here, yes, that's smooth and continuous until I get to 4, and then I can walk on this graph all the way down to -infinity. Well, that didn't work very well. So I can say the domain of f neg 1, or not, I keep saying f neg 1, f dash of x, definitely not f neg 1 of x, is going to be all real numbers except for the values of 1 and 4. And be careful that you use the correct brackets, the squiggle brackets, because it's only the values of 1 and 4. It is not, if you write it as r excluding 1, 4, then you're saying the values in between. Or hard brackets, the same thing, you're just including 1 and 4. So you definitely don't want that. Make sure you've got the squiggle brackets. So smooth and continuous for a gradient function to exist. Let's move on. A last example. All right. Consider the function this, f of x. The graph of the function is shown. Okay, fine. Find the equation of the tangent to the curve at the point 4, 6. Okay, let's draw a picture. They've already given us the picture of the curve. I'm going to draw the tangent on. So I might use that handy ruler. 4, 6. All right. So 4, 6, let's say it would be nice if the picture was a little bit bigger, but it'll do. All right, so I'm going to draw the tangent here and get rid of the ruler, and let's say that's the point 4, 6. So I think it's a good idea to draw a little representation of it, a representative diagram. And we're trying to find this, y equals mx plus c. A tangent is a straight line, so y equals mx plus c. Write it there, it'll give you a clue. Find the equation, okay, find the equation of tangent. All right, so, well, y equals mx plus c, we need two things. We need a gradient and we need the point. And here's the big idea of a tangent. So I'm going to write it over here, and you definitely would have done this in year 11. There's two important things. One, it has the same gradient as the curve at that point. So clearly, your tangent line at the point 4, 6 is a very different line to the tangent at, say, let's say there's a point. Let's do this one, 3, 0. So that would be the, well, actually that doesn't look very good, but just pretend that's the Actually, don't pretend I'll move it. Let's put a tangent here. So just say you've got a tangent at this point here. Well, your line, the green line and the orange line are very different. They have completely different gradients. So obviously the green line has a positive gradient, the orange line has a negative gradient. So the tangent has the same gradient only at that point, and it doesn't matter if it's just a really close by point, it won't have the same gradient. So it's just at that point. The second thing about a tangent is, and this is really obvious, it shares the point. So our tangent has a 0.46, and so does the curve. It has a 0.46. So let's find the gradient of the tangent line, and knowing that it has the same gradient as the curve. So f of x equals 1 minus x, x minus 3, x minus 6. I'm going to expand that. It's a little bit annoying because it's 3 brackets. 1 times x is x, 1 times neg 3, neg 3. Neg x times x, neg x squared. Neg x times neg 3 plus 3x. Okay. All right, this is going to be neg x squared, 3x plus x plus 4x minus 3. Neg x squared times x, neg x cubed, neg x squared times neg 6 plus 6x squared. 4x times x plus 4x squared. 4x times neg 6, neg 24x. Neg 3 times x, neg 3x. Neg 3 times neg 6 plus 18. And look, what is a common mistake here is that people are going to think I've done so much work. Well, you know, I've already differentiated it. And really, you're not even going to give it that much thought. But the point is, we've done all that work. People are going to think this is the gradient function. It's not. F dash of x. And the way I prevent myself from accidentally doing such a silly mistake is to write f of x on every line, so that then when I truly do change it to f dash of x, I know that I've got my gradient function. So I've just differentiated that in the usual way. Oh, I think I've done something weird there. That's not 6x squared, it's 10x. Sorry, hold on. I'll just stuff that up. So I should get neg 3x squared. Yep. 2 times 10 is plus 20. X minus 27. Yeah, that's better. All right. So now that I've got my gradient function, I need to find the gradient when x is 4. So remember, we're finding the gradient when x is 4. So now I can just do that. That's actually pretty easy. F dash of 4 equals neg 3 times 4 squared plus 20 times 4 minus 27. Neg 3 times 16, that's going to be what, negative 48, plus 80 minus 27, neg 48 plus 80, we're going to get to 6. No, we're not going to get to 6, are we? We're going to get to 5. And look, it probably, it doesn't matter, 5. Okay, so the gradient is 5. So far we've got y equals 5x plus c. So we're almost there, but obviously we need to find c. And this is really the easy part, but so don't leave it at this. If we've got y equals 5x plus c, then we know it shares the point. So we've taken into account this rule. It has the same gradient as a curve at that point. Done. Now we need to go, it shares the point. So if it shares the point, we're subbing in the point 46 to find the value of c. So that's an xy point on the graph, the coordinates there. 6 equals 5 times 4 plus c, 20 plus c, and c equals neg 14. So my final answer will be y equals 5x minus 14. And look, you could use the equation y minus y1 equals mx minus x1 in your working out. That's fine, and you'll get the same answer, albeit it could be a different form. I like to use y equals mx plus c, and I pretty much always use y equals mx plus c. But as I said, if you want to use the other equation, that's fine too. So that takes us to the end of the many examples from exercise 5.2, review of differentiation.